So my topic here is about magnetic transport in quantum systems. The question is about how we can transport, because magnetic field tends to localize particles. Classically, we know that if we have in two-dimensional particle which is charged and put it into a homogeneous magnetic field, it goes over cyclotronic orbits. In quantum case, then you have the magnetic Laplacian, and as it is well known, the spectrum consists of infinitely degenerate eigenvalues, the Landau levels, and the eigenfunctions are just the eigenfunction of the 2D harmonic oscillator properly shifted. Now, in order to make the particle moving, you need to present or to include some obstacle. And the obstacle can be of various kind. The obstacle can be the variation of the field itself. So the classical example is what people call Iwazuka model. If you take a magnetic field which the homogeneous field which is perturbed by this function Bx, which depends on one variable only. I mean, it has translation invariance. So then the trick which we will be using during this talk is you can take a partial Fourier transform and write the operator as a direct integral with the fiber, which is this operator. And now it is conjectured that if B is non-zero, then the spectrum would be always purely absolutely continuous, which is a spectral expression of the transport. To this day, this conjecture is open, but there are various sufficient conditions under which is true. Here are some examples. But okay, so the perturbation which causes a transport could be a lot of other things. If you put it in an obstacle which is of a potential character, of course, the easiest thing would be if you take a single Schrödinger operator and you take a delta interaction on a curve. So if the curve is finite, then you get the spectrum which will be now again pure point. That is, the Landau levels may split into clusters of eigenvalues of finite multiplicity. They may be also preserved depending on the shape of the curve. And in order to make the spectrum absolutely continuous, you need to make the perturbation infinitely extended. So the easiest example is if this curve gamma is a straight line. So then, of course, again you use the Landau gauge, and then the operator looks as follows. And you can again use the partial Fourier transformation in the variable which corresponds to the direction in which it is translation invariant, and you get the fiber operators of this type. And now the question: what will happen with the Landau levels if you include this perturbation alpha? You can easily see that this eigenvalues as a function of the momentum p are nowhere constant. Here are some examples. If you change alpha, positive alpha, smaller, larger, still larger, you see that they change this way. You know that if alpha is large enough, you see this envelope curve, which looks like the dispersion curve if you have a magnetic field in a half plane with the Dirichlet condition. But still, there are some gaps, and of course, one guess is that the gaps are always open, but this is not proved. If you get the same with the negative alpha, then of course the eigenvalues are pushed back, and they go like that, or like that. always, again, these are not crossing, they are avoided crossings, and again, you expect that the gaps will be open. Now, you can, of course, that was an extreme, a very simple example. You can ask what will happen if you get a potential perturbation like that. And then, of course, in contrast to delta, you have to impose assumptions on the potential. So the basic assumption here would be that the positive part is locally L2 and the negative is something like that. If you have this example, then you guarantee that the fiber operators which you get after the decomposition into direct integral have discrete spectrum, and the eigenvalues are a function of P. And the question, of course, is whether these functions are non-constant. In fact, the discrete character, if the potential would be something which goes to infinity, then the discreteness would be guaranteed. But you can have also potentials which are oscillating, but under this assumption, it's still the spectrum is discrete if you use the Molchanov's criterion. So in order to get the absolute continuity of the spectrum, you need two things. You need to check that the family is analytic with respect to the momentum variable P, and that no eigenvalue branch is constant. And if the functions are analytic, you can it's just enough to show that they are non-constant on any interval. So the easiest thing if the potential, which the perturbation is asymmetric, that is, if you have different limits and plus and minus infinity, because then you have an analytic function which has two different values and therefore is non-constant. That's easy. What is more difficult is if your perturbation is local. I mean, your potential perturbation vanishes at infinity. And then, there are various conditions you can derive. Now we strengthen our assumption. We will assume that the potential is just L2. And then the first claim I can make is that then the spectrum is, under this assumption, the spectrum is absolutely continuous for up to certain value. That is the finite number for any finite number of these functions. There is a critical constant lambda, critical constant lambda for which the eigenvalues corresponding to lambda times the potential are non-constant. For that you need just first to show that under V2 the limits of the dispersion function as plus and minus infinity are the same, which is a standard Kato type argument, and then you use just a perturbation theory. So there is a Landau level and the first order of the perturbation theory, and now if you need to have this non-zero, then you know for a lambda small enough, this will dominate over this term, and then you will have a non-constant function. So here it is easy because now this is a convolution, and the convolution, if you use the bijectivity of the Fourier transform, so the Fourier images, the Fourier image of this is just the product of the Fourier images, and these functions, you know, that's just eigenfunctions of the harmonic oscillator, and they are they may have zeros, but they are non-zero everywhere, which means that the Fourier image of this thing is non-zero everywhere, and therefore you have what you need. And of course, this is valid for any j. So if you have a finite number of j's, you change just a minimum of the lambdas, and you get the claim. Before proceeding, just the example which does not fit when the potential is something which is unbounded. and behaves like that. And that is, roughly speaking, it's a combination of electric field and a magnetic field. So if you have a purely electric field, this is absent, you have just alpha, then it's just the shifted harmonic oscillator, and you will find explicitly that the functions are like that, which means that the spectrum is purely absolutely continuous, and the threshold is shifted down by the presence of the electric field. If you have a purely magnetic case, the perturbation is magnetic, so this is not here, this is here, then it depends how strong this perturbation is. If the magnetic field wins over that, you have this inequality, then you have again an explicit formula for this, and you have the spectrum which is purely discrete, and the spectrum is absolutely continuous, but now it covers the whole real line. Well, if the field is weak, then there are no states which are localized in the vicinity of the barrier. Okay, one more result of this type. Namely, if now you make a stronger assumption of the potential, you will assume that the C1 and the derivative is L2. Then the claim is under this assumptions, the spectrum is again absolutely continuous. And how you do that? Again, a perturbation argument, but this time it's Feynman-Hellman. That is, you can you know that the function is analytic, and you compute the derivative, which is like that, and the same argument. But now you don't know, of course, these eigenfunctions, but you know that in order to Fourier image of this would vanish in an interval, it would need that the function is oscillating, but we know that the function is a nth eigenvalue of a Sturm-Liouville operator that is a finite number of zeros. So with reference to some standard result, again you prove that this is a non-zero quantity. And you can use it if your potential perturbation is sign definite. You can find something which is of the previous type, that is smooth function, and using a minimax estimate, you prove that then the spectrum is again absolutely continuous. That is, no eigenvalue branch is constant. But you need that the minimization, there is an interval when you can minimize or maximize this function by a smooth one. An example why this is not the case, or it may not be the case, you take the fat Cantor set. The Cantor is usually throw up 1/3 to etc. Here you throw out smaller interval, 1/4, 1/16. So you get a function which is well, the non-zero on the set of positive measure, but it contains no interval. So that's a counterexample. Okay, so this came from this recent work with my student, and there are of course various questions. The first one. And the most important one is of the type of this Iwazuka type conjecture. One would expect that the function, if the perturbation V is translation invariant and non-zero, that any such perturbation would produce absolutely continuous spectrum. But again, this is an open question and challenge to everybody. Now, in the rest of the talk, I will now talk about transport which has no classical analog, because I mean, if you have a potential ditch and a magnetic field, classical particle also transports. Yeah, it goes because the cyclotonic radius changes, larger, smaller. In this way, it propagates. The most dramatic is if you have a potential which is positive, negative, the orbit is just a snake. But there are systems where you have quantum mechanical transporting particle, even in the classical particle does not move. Here is one easy example. If you take just a Laplace-Hallmian, but instead of a potential, you take an array of delta potentials. So classically, nothing happens because in order to transport, the particle should hit the point and be reflected. But the classical probability of hitting a point, of course, is a zero measure event in the phase space. But if you look at the quantum mechanical system, that is, you take Laplace-Hamiltonian with this. Now, I write this perturbation like that, but of course it's just a formal expression because the two-dimension or three-dimensional point interaction is not an additive perturbation. It's in fact a self-adjoint extension. It's something, and you see that because the conditions we described that cannot be written in this form. It's a standard matter which you can find in the classical book by Alberio and others. Now, how the spectrum looks like. Now, the Landau levels survive because you have solutions which are signs, and if you arrange the signs so that the zeros are at the point of the delta functions, the solution is still there. But in addition, in between any pair of the Landau levels, there is one interval of absolutely continuous spectrum. So that's an example. That's an example how you do that. Again, you take the Floquet decomposition. You study just one strip with the quasi-periodic condition and 1 point interaction, and using the Crane formula, you find that there is an eigenvalue which depends on the quasi-momentum variable. Okay. Two other examples. One is magnetic layers. So if you take now instead 2 dimensions here and 3, you have a layer which is flat, and you have a magnetic field which is perpendicular. So as long as the layer is straight, nothing interesting happens. You simply separate variables, and you get a spectrum which is a combination of Landau levels and transverse eigenvalues of the Dirichlet Laplacian. So my question now is, if you geometrically perturb the layer, say I bend it, what will happen? Something like that. Again, the bending will be translation invariance. You take but it is symmetric with respect to shifts in this variable. So this is a cut of the bend layer. And you can parameterize it. You take the axis of the layer. That will be such a curve. We suppose that is smooth enough that it's you have a curvature here, and the curvature is given by the standard way. You need the curve is C2, and then the usual trick is that you can pass by a unitary transformation to a straight layer by using the orthogonal coordinate, I mean the length and the perpendicular. And if you do that, you get, of course, you have to suppose that if you bend it, that it does not intersect itself. And you prove that then it is mapped to have operator in a straight layer. But now the longitudinal part is modified with this thing here. It's 1 minus the curvature, and A is the half width of the thing. And what is most important, the curvature will give rise to an effective curvature-induced potential, something which is the dominating term for thin layer is just the multiple of the skirt curvature, and there are 2 other terms. And now you want to see whether this operator has a spectrum which is absolutely continuous. So what you will do is, again, you use the partial Fourier transformation in the variable along the perturbation. You write it as a direct integral, and here is a fiber operator. And in order to get the absolute continuity, you need 3 things. You need first to check that this is an analytic function as a function of the momentum variable. that the spectrum is discrete, that the resolvent is compact, and that no eigenvalue branch is constant with respect to the momentum variable. So you can find various sufficient conditions. Here are two of them, either one-sided layer or a sort of compact band. Maybe I will show you better the pictures than the pictures are here. Oops, sorry. So either you have so this is the direction of the field. So if you bend it like that, independently of the width of the layer, of course, which respects the smoothness of the boundary, then the spectrum is absolutely continuous. And the second condition say if you have the asymptotes which are not parallel, then the spectrum is absolutely continuous, provided the width does not exceed something. There is an explicit formula for the critical width, but it's cumbersome. I do not show it. And the natural question is again the Eva-Zucker time conjecture again. That is, does any non-trivial band of such a layer produce an absolutely continuous spectrum? If not, what are the necessary conditions?
Excuse me, and what does asymptotically means? What is the parameter of asymptotics, or it is for large?
What asymptotic?
An asymptotically flat layer.
Asymptotically, that is, you have something which is curved and asymptotic is straight. Yeah. The easiest thing, you have just the bend in a compact region, and outside is just a flat layer. Yeah. Okay. So now one more thing you can go, if you consider thin layers. That is, you take again the curvature which is bounded, and you know that if you take the curved layer and shrink it, you get a two-dimensional operator, and the leading, as I said, the leading term in the potential was just the multiple of the curvature. So you get effective operator like that with something which is something which represents the magnetic field influenced by the curvature. And now for this you get now another condition. So if the layer is thin, then below you choose the energy E, and below this value the spectrum is absolutely continuous if you assume that this is true. So again, better to illustrate it by a picture. So either it's just a local bump, local bend in the, or you have something which is straight to the left to the point, and something to the anything to the right. Okay, now my last example, but first an intermezzo. Now you take again a flat layer, and instead of Dirichlet condition, you take a Neumann window. You get a strip, infinite straight strip in one boundary, where you replace the Dirichlet condition by Neumann. So then, and you have a magnetic field which is perpendicular, and what you can do, of course, is again to use the partial Fourier. So you reduce your problem to a strip, two-dimensional strip, Dirichlet, and in one of the Dirichlet boundaries there is a Neumann window. So then without the Neumann window, the spectrum is just this thing here. You know, even the eigenfunctions, which are just the oscillator eigenfunctions, timed the eigenfunction in the transverse direction, and the proportion, the dispersion curves, how they behave. If you introduce the windows and they are monotonous in the window, if you expand the window, the eigenvalues go down. Then when the momentum goes to plus and minus infinity, they go to the Landau levels, or the shifted Landau levels. That's this, and the Neumann window puts the eigenvalue down, so you have curves which are something like that. And well, this family is again analytic, and as a result, you have the theorem that you have now the spectrum consists of spectrum of this system consists of bands, At the upper end of the band, the upper end is where the original Landau level was. There is a continuity with respect to parameters, and there is as a function of the width, the band width is decreasing, so the band is going. So for small enough, there is an open gap, but it may close. So I briefly show you the application. So if you have two layers and you have a window in the layer, so you have you have two situations. If the band is if the two layers are the same width, then you have the spectrum which is Landau levels, and from each Landau levels spreads a band. If you instead has an asymmetric layer, then it depends on now the ratio of the sides. If it's irrational, the spectrum is purely absolutely continuous. If it's rational, there are some Landau levels surviving, and the rest is the absolutely continuous spectrum. And the last thing, it's a purely magnetic transport, because if you look at the eigenfunctions, then you see that if change the sign of x and change the sign of p, you get the same. That is, the transport goes along one boundary of the window there, goes along the other boundary there. Okay, so that is the thing. And of course, if the window is broad, then you may ask what will happen if you have such a system. So then, of course, the spectrum would be absolutely continuous, because you have the different limit to the left and right. And the question rather is what will happen whether the system or the spectrum can have gaps. And the question is, or the answer is, if B is large enough, there is at least one gap in the spectrum. Again, you have the same effect, that is, if the ratio of the width is rational, you may have some Landau level surviving. If it's not, the spectrum is absolutely continuous. And you have many questions to ask. For example, what is weak coupling? What is the asymptotic? How the bands behave when the window goes to zero? What are the properties of the spectrum? Other geometric, so instead of bending or making window, you can make a local deformation. That's an open. And probably the most important for the application in condensed matter physics, it's the impurities. That is, if you add a noise, which part of the absolutely continuous spectrum survives? It is well known that if you have a Dirichlet boundary, say in the half plane, if the impurity is weak, then the spectrum would have dense pure point parts, but part of the absolutely continuous spectrum survives, and it dies when so the question is, what will happen now? It's completely open. So as you see, there are many open questions, and I think that's the best thing to end up. Thank you.
Thank you very much.